Take a look at this yellow Tesla phone manufacturing plant. At first glance, it appears flawless. The depth of field mimics a professional lens, and the semantic details, like the people in the background, seem convincing. Modern synthetic image generators have decoupled these superficial semantic artifacts from actual physical invariants. They produce textures that easily pass human inspection, but they lack an underlying world model. Look at this visualization of light rays interacting with a synthetic 3D object. Despite the surface realism, the model fails to simulate energy conservation. The collision dynamics and multi-source light reflections fracture and bend at impossible angles. An academic paper recently published on alphaXiv, titled Aletheia, addresses these failures by introducing a concept called resonance consistency loss. The researchers demonstrate we must evaluate the structural logic of an image, not just its pixels. Their system flags generative models when they hallucinate physical states that simply cannot exist in reality. While Aletheia is a significant step forward, it relies on standard true score functions and traditional pairwise graph structures. Calculating physical relationships using these traditional methods creates a massive computational bottleneck. To build a real-time, deployable forensic engine, we must upgrade the structural reasoning layer entirely, fusing the physics-based VITA-VQ protocol with a reactive Directed Acyclic Graph environment. Catching these hallucinations requires a rigorous audit of the scene's internal physical logic. This schematic shows a standard dyadic graph mapped onto a face, where edges connect exactly two nodes. But at scale, calculating every pairwise relationship across a high-resolution image creates a dense, chaotic mesh, far too slow for real-time analysis. Furthermore, a pairwise graph averages out errors. If the lighting vector is mathematically sound, but the resulting shadow cast is incorrect, the system outputs a passing score. The Decessoret protocol solves this with the VITA-VQ algorithm, upgrading the architecture into a hypergraph. Instead of isolated lines, facial features and lighting vectors are grouped into a single entity called a hyperedge. This polyadic topology reduces the computational complexity to a near-linear scale. It forces the system to evaluate simultaneous consistency across all physical laws at once. Authenticity is a property of the whole set. By shifting to complete structural ensembles, a single physical flaw can invalidate the entire object. Standard transformer architectures operate on additive, residual learning. They use softmax attention to greedily predict missing information and attempt to fix the data path. The active reasoning layer of the VITA-VQ framework uses a completely different architecture, the self-correcting delta transformer, or SCDT. The SCDT is strictly subtractive, prioritizing the preservation of truth over the prediction of missing data. Here, an incoming error vector, a high-entropy signal, is multiplied by a householder matrix operator. When the SCDT identifies a conflict within a hyperedge, this mathematical eraser gate isolates the error and annihilates the entire node path. The system makes no attempt to reconstruct or fix the fake pixel data. It simply erases the faulty reasoning path from the latent manifold entirely. The SCDT enforces a strict zero-trust environment, ensuring the machine never drifts into hallucination space to accommodate a deceptive input. We can translate this theory into a tangible tool for the alphaXiv and marimo molab notebook competition. Traditional Jupyter notebooks suffer from hidden state and execution order problems. Static cells hold on to old data, which frequently breaks complex forensic pipelines. Marimo is built differently. It operates as a reactive Directed Acyclic Graph, or DAG. This guarantees that code, outputs, and the program's memory remain perfectly in sync. This DAG architecture allows us to build a live UI. Updating a variable through these sliders instantly triggers downstream matrix operations via local MLX processing without requiring a single callback. This environment transforms the static resonance consistency of the Aletheia paper into an executable continuous forensic loop. By pairing polyadic math with a reactive DAG, visual forensics moves from an academic post-mortem into real-time interception. We can test the efficacy of this system using the first interactive axis on our marimo dashboard, the energy thermometer. Watch what happens as we push this slider up. It increases the sensitivity of the VITA-VQ energy gradient proxy. which scans the image for causal violations and depth mapping failures. But this creates a critical edge case. If the protocol only stands for strict physical invariance, how does it process abstract human art, like a constructivist poster or a Dadaist photo montage? This is why we have a second interactive axis, the creativity gradient. In this image, we are looking at a physically impossible piece of Dadaist art, but the very graph overlay is glowing a primary green. This horizontal slider acts as an artistic allowance threshold. It globally dampens the physical heat map to mathematically account for intentional structural violations. Manipulating these two sliders gives a forensic analyst the ability to actively isolate the difference between a deceptive generative hallucination and genuine artistic expression. The VITA-VQ protocol inside Marimo provides a transparent, verifiable topology of truth, measuring both the hard physical evidence and the margins of human intent.